solution for problem Roaring Years, which is the second one of round 1C 2021 Codejam. The problem statement gives you a number and you have to tell the next special number from which is larger than that number, strictly greater than that number. And how they have defined a special number is that a number is a special number if it is formed by the concatenation of two or more consecutive integers. So if we have an integer, say 23, the next integer is 24, and if we join them together, which means we concatenate them, 2, 3, 2, 4 is a special number. We can join multiple integers as well, 25 and then 26. So this is also a special number. It's a big special number. Well, obviously single special numbers don't exist. So if you just say that only that is I will only take 12 and this is a special number, then this is a special number because it's 1, 2. But if you take 13, this is not a special number because you have only taken a single number, and if you were to do that, every number would be a special number. So if you add the next number to it, which is 14, this is a special number, then you can add 15 and then so on. So you have to concatenate consecutive numbers to make a special number, and the problem will give you one number which may or may not be special, and you have to tell which is the next special number from that number, which is strictly larger than that number. Now the inputs can be of the size 10 to the power 18. So for the first test case, the inputs are small, so you can generate every possible special number up to 10 to the power 6, and then you can just check. But since this is very large, we cannot do exactly this, but we will take some inspiration from test set 1. So let's see how to do this. So to generate a special number, we concatenate multiple consecutive integers. So you see that when we choose the first integer, which we'll start with, let's say we'll start with 7, the only thing remaining is for us to decide the size, because we cannot do anything else. We can keep adding the next number. So 8, 9, then we dial 10, then 11. We'll have to decide where to stop. So this is the number. So see, it was decided only by the first starting digit, which is 7, and the size, which 7, then 8, then 9, how many numbers you want to add. So you can see that these numbers grow very large. Whenever you take a number and you concatenate the next number, the resulting number is at least twice the original number, the size of it, which means that it's roughly more than the square of that number, because the square of a number has in most of the cases the size double of that number. By size I mean the number of digits. So for 10 to the power 18, square root of n complexity is not possible, but cube root of n is manageable. So if we can create a set of all such special numbers which are formed by concatenation of 3 or more consecutive numbers, because the first number from where we start cannot be more than 10 to the power 6, because if we take a number which is like 10 to the power 7, then if we add 2 more numbers, and they will be of 7 digits because they are consecutive and the first number is of 7 digits, so the next 2 numbers must be of at least 7 digits, so the total would be 21, which is more than 18. So if you concatenate 3 or more numbers, then the starting number can only be up to 10 to the power 6. So we can generate all special numbers where the first integer is some number, because it's only up to 10 to the power 6, so we can do that. But we can only not do the case when the number is formed by concatenation of only 2 consecutive numbers. We'll handle that particular case separately. Other than that, every other number will generate. So we'll generate all special numbers which are formed by concatenation of 3 or more integers, consecutive integers. You can see that the first integer cannot be more than 10 to the power 6, so those numbers would be limited and we can form them. And after that, for the case where the number is formed by the concatenation of only 2 consecutive integers and the starting integer can be up to 10 to the power 9, we'll handle that case separately without actually generating the numbers, but we'll search for it using binary search. So let's first see how to generate and store all special numbers where the starting integer is something and it's at least 3 concatenations, so at least 3 consecutive integers are concatenated, and the resulting number is less than 10 to the power 18. So the special number is has less than 18 digits, 19 digits, less than or equal to 18 digits in it. So let's see. So first of all, this is my code. We do some pre-processing where we'll generate all special numbers which are formed by the concatenations of 3 or more consecutive integers. And since the upper limit on that resulting number is 10 to the 18, we only have to loop to 10 to the 6. So this is that limit, 10 to the 6. What is this? I'll explain it in a while. So 10 to the power 6. So in pre-process, which is here, I loop from 1 to 10 to the power n, and then size is just the number of digits, so I can do it using toString size. This is the number of digits in this number, and this is the number of this is the 1 plus the number of concatenations. So this I have a make function here which takes a string, and the string must be of size up to 10 to the 18. So this STOLL, string to long, this function converts the string into a long integer, and then n times I concatenate. So I concatenate n times. So for 3 consecutive numbers I have to concatenate twice, because the original number plus 1 concatenation plus another concatenations. So n should be 2 for the minimum thing. For 3 consecutive numbers n must be 2, because I am concatenating n times. So when I concatenate 2 times, I have 3 integers together. So I am going to append this and I am going to return it as a string. So this is the thing. So I concatenate it, and when I concatenate it, the size grows by j plus 1, where j is the number of concatenations. So if I concatenate once, the size is doubled. If I concatenate twice, the size is tripled. It can be more, but if the number is on the edge, 9999, and then the number is bigger, but we'll handle that also. So size into j plus 1 is at least the size, and it should be less than 19 digits, because the number can be only 10 to the power 18, so 18 digits only. So I create this using the function, and if the size is less than 19, which means that the number is of up to 18 digits, can be stored in a long and is of our use, I insert it in my this set, which is a set of longs. LL means long. So all. These are all numbers which are formed by the concatenation of 3 or more integers. So I put them all here. Now only those numbers are remaining which are formed by the concatenation of 2 integers. Other than that, all other numbers are in this set. So first I pre-process this here. I pre-process this and then I run the test cases. So now I have to find the twice concatenation, and now let's see. Let's say we have a number x, and if we concatenate x plus 1 to it, so the resulting number would be these two joined together. It is easy to see that if we choose bigger x, this resulting number will also be bigger. This is pretty obvious, because let's say if we choose 8, 9, and then we choose 9 and then 10, this number is obviously bigger than this number, because the leading digit is obviously larger, the leading part, and if not larger, then the size is larger. So the larger x is, the larger we get. So we can binary search. This is a ascending operation, so we can binary search over all the numbers. So what I do is this find thing, sorry, not the find thing, this here it is, this tell thing. This binary searches over the entire range and tells me whether which is the just the largest number, the largest special number which I can form using only 2 concatenations. 1 concatenation means 2 consecutive integers, so only 1 concatenation of 2 consecutive integers. So what is this? It binary searches. So m is my x, so I take m, I take it as the middle point, and then I just concatenate once. So I use my function which I made before, and I get a string. I'm not converting them into longs because the size can be large, and that will throw an error if it cannot be stored in long. So I am comparing them as strings itself. So you cannot just use the equality operator. This will tell you lexicographically larger string. So first you have to compare the sizes. So if the resulting size is greater than the size, so this greater than operation in string will say that 1, 2, 3 is smaller than 4, because the first thing it compares it like an alphabet. So this is not true, but the string operation tells it that because this number will be before this number in a dictionary. That's why the string, you cannot use the comparator directly. First you have to compare sizes. So once you compare the sizes and do the binary search, after that you can compare them like strings, because if the sizes are equal, the lexicographically smaller number will be the smaller number mathematically. So you do this, it's a simple binary search, and the answer is the smallest number of the form x into x concatenated with x plus 1, which is larger than the given number x, the smallest such number. See, if it is strictly greater only, then I am setting it to the answer, and then I'll return it. So for this single concatenation, which is 2 consecutive integers, I used binary search, and for 3 or more I actually generated them. And you can do that, you can even binary search for them also, but you can also generate them, because then it goes down to cubic complexity, or sorry, cube root complexity, and that is manageable. So I generated them and I created them. Now one case is remaining, and that is if the number is at the edge, which means that if the number is 9999, so many nines, such that I have not stored it in the set, it's 19 digits. So if it's 18 times 9, let's say, or rather 17 times, I think, no, 18 times 9, because 18 digit, less than 10 to power 18 means 18 digit number. So at the very end, that number needs a number which is more than that, and that I have not stored in the set. So I created this big, this is the smallest number of 19 digits, and you can pretty easily see that it's 1 2 3 4 5 6 7 8 9 up to 14. You can convince yourself that this is in fact the smallest number of 19 digits, cannot be stored in a long, which is special. So this is for the very last cases, where the number is at the very extreme, the largest. If the input is say 10 to the power 18, then what will I do? I'll do this. That's why I have made this separately. So this is the binary search thing, and then I have this create function also. I just realized that it's not necessary, but one candidate, you can also think that if the number is n digited, let's say n digited number, what is the smallest n plus 1 digited number which is special? So for that you just find the first factor of n plus 1 and you do that many times. So it's either 10, 11, 12, 13, or it's you find the smallest n plus 1 digital number, which is not necessary. But I did that at that time because I did not think it through completely. But this is not necessary, but you can also do it. So we have 3 candidates. First I find the upper bound on x, which is all the numbers which I have generated. And if this is all.end, which means that I have no number which is larger than this number already in my set, that then I have initialized it to big. So this number, this here. And also I do the binary search thing, and in the binary search as well, see, I have initialized answer to big, because if I don't get an answer, which means that the answer is too big from 18 digits, is larger than 18 digits, which means that it must be the smallest number of 19 digits, because the input cannot be more than 18 digits. So I have done that, and then I take the minimum. For minimum, you once again have to do the size thing, that you cannot directly compare strings, then it will tell the lexicographically largest string. So you have to find the size. You first have to compare the sizes. If one string is larger than another string, then no matter what, that largest string is bigger in mathematically. But if they are equal, then you can do the inbuilt greater than thing of strings, lexicographically comparison. So then you print the smallest of all of these 3. Once again, this is not necessary. This create one, can one, this is not necessary. I'll keep it here, but you don't have to do it. This just finds the smallest string of size n plus 1, which is special, where n is the size of my the number of digits on my input. So if the input was say 9999, earlier I was having some trouble with the edge cases, so I generated a new number which is one more than that. But you can also get it using this binary search thing, so that's fine. Now let's check it on the input. So when we run it on the input, see, it takes some time, but that's fine, because the limit is 30 seconds, so it took very less than 30 seconds. And as you can see, the input matches. And to show this, I can also submit this here. So we'll recap it while it judges. So what we did was, since we can actually generate all such special numbers which are made by the concatenation of 3 or more consecutive integers, because the first integer of them must be 10 to the power 6, at least at most 6 digits, so it must be less than 10 to the power 6. So we can do that. So we generated all those because that was possible. But for the 2-digit thing, the 2 concatenation, which is just 2 consecutive numbers, just 1 concatenation, we cannot generate them because they will be of size 10 to the power 9, much larger in space and even in time. So we cannot do that. So for that we did binary search, because we can see that concatenation of 2 integers is the resulting integer, which is formed by the concatenation of 2 consecutive integers, is an increasing function, it's an increasing sequence. So you can just binary search over it and then you can find the final thing. So as you can see that the sample and all the 2 test sets have passed. Thank you for watching.